who is now a postdoc in Antwerp, Aldo Witte. That's the ArXiv number. I was checking the paper yesterday, and suddenly I started seeing that the version we published, and probably even the one that we sent to the journal, still has some comments that we forgot to remove. Anyway, they're bright red, so it's easy to miss. Anyway, so thanks for the invitation. Maybe just like something else. Back in Utrecht, I'm in charge of a course on presenting mathematics, so the master students have to do that. So I give them all sorts of hints, like really practice your presentation, have it nailed, get it on time, know what the slides are coming, so never be surprised by a slide. For example, I didn't know it was coming, so you cannot imagine how nervous I am to be here right now, because it's being recorded and they can see it. Ruining my reputation, that's already not very big. So anyway, there is that. Before we go to T-duality, there's just a film that I would like to share with you guys. So it's from Peanuts. And the context is a decathlon, and it's the last part of the decathlon. It's a bit competition between schools. And this is the situation there. They're going to start racing, and there are 1 point, like whoever wins this race wins. So I like that because also illustrates this tendency that mathematicians have, that they kind of start seeing some physics. And it's like, oh, this is so nice. And they start thinking they understand it. And then they take a tangent and they just run with it. I may be doing that today, so I don't know. So that's just something to be aware of. But it's something that I see often anyway. So I identify myself with that little clip. Anyway, so T-duality. What is T-duality? Well, it's something that comes from physics. I don't know what it is, but apparently it started only in '87, which I was really surprised by. I thought it had been there forever. It feels like it has been there forever, and apparently it's this Satya Palan who figured out that in a very simple model compactification in a circle, you could do two things at the same time that cancel each other out. You could invert the radius of the circle and swap winding and momentum. And what I hear from physicists sometimes is that this thing of swapping winding and momentum is something to do with exchange of tangent and cotangent directions, which, if you ask me in 2000 or 2001 or something like that, it made no sense whatsoever to have cotangent directions. But somehow it's something that physicists already made sense back then. This was really like a very simple model. It's not a very cited paper, probably because of this issue that it's just on a circle and there is not much consequence except for the fact it's the same physics. But people picked it up, and one thing that people like to talk about is like, what if you had a metric, if you had not just a circle, but a manifold with a circle symmetry, and you had a metric, so you can write your metric, assuming it's invariant, you can write it in this term here, so you pick a connection, at least locally you pick a connection. So this G0 is somehow to do with the radius of the circle, and you have these other terms which have to do with how horizontal, what you describe as horizontal directions pair with the circle directions. You can even turn on a B field, and this is what the T-dual metric looks like. So you see that the inversion of the radius appears here in the top coefficient. Oh, I have this thing here. The inversion of the circle appears here in the coefficient of this guy. And if you happen to have a B field and you happen to have a G, then they can influence the rest of the metric in a number of ways. But if you had no B field and you had picked the connection that comes from the metric, then this bit here would be 0, This bit here would not be there because you pick the horizontals to be the metric horizontals, and all you're going to see was really the inversion of the circle. You do not get a new term on the B field, the B would remain 0, and you'd invert the circle and just get the G2 back there. So that would be all that you'd see. But if you have more tensors, if your metrics is a bit different, then you get all that. And this go by the name of Busher rules, but in fact, a whole bunch of people study these kind of things. T-duality has a few other people who really contributed to it, and because Roll is in the audience, tada. Rocek also had a whole bunch of things to do with it. I think he was the supervisor of Busher, right? And whoever's not in the audience didn't get mentioned, but there are more people. So it's something that's very well understood by physicists, and apparently when you propose a model, you'd like to be diffeomorphism invariant and T-duality invariant. It's like one of the basic symmetries that you impose to check that your model makes sense. Mathematically, things get more interesting in 2003 when Bochnak, Evsling, and Matai proposed this topological T-duality. So instead of being like local in a neighborhood of a fiber, that's a bit what the Busher rules are, you start getting these things which is about how the overall topology of your space behaves when you do T-duality. What they observed was that you could exchange the H-flux with the curvature. So out of something with 0 H-flux, but with curvature, do a T-dual that has H-flux and no curvature and vice versa. So there is like an interesting global behavior going on with T-duality that maybe you'd miss if you just had Busher rules, for example, if you're just looking in neighborhoods of orbits. So they did a whole bunch of things there. One of them was the existence of T-dual. So for example, if you have a circle action, you always can produce a T-dual. If you have a torus action with more directions, then there is a condition on the H-flux that will allow it to produce T-duals. There is some question about what if there are more, like if the H-flux does not satisfy that existence condition, what would be the T-dual? They start proposing other stuff, a bundle of non-commutative tori and stuff like that. But at least they tackle the existence of the T-dual, and the language that they use is really the T-dual because they have an explicit construction, like you make these choices and you get a T-dual, so we know that it exists. And of course, just constructing a new space is a bit boring. You'd like to say that the new space that you constructed is related to the original one that you had. And in this case, the relation is given by twisted cohomology and twisted K-theory. So they prove that the two spaces which are T-dual have isomorphic twisted cohomologies and isomorphic twisted K-theories. So there was a relation between them. So that was a very positive thing. And essentially, it made it more mathematically treatable, having this approach which was global instead of just local. The question of uniqueness came back a couple of years later with Bunk and Schick. They look at the papers by Matai and so on, and they realized that, okay, they made some choices and got a T-dual, but I could have made a whole bunch of other choices, and I could have got a whole bunch of other T-duals to the same space. So there's no uniqueness here. So if somehow in your mind, the T-dual, what we like to say, and I probably will say the T-dual many times in this talk, but if you think of it as being a unique space, you should get it out of your mind. It's a relation. T-duality is a relation between spaces, and there can be many T-duals to a fixed space. I'm going to see a little bit about that later as well. So no uniqueness already in the standard T-duality case. With the context of generalized geometry, we realized that this exchange of tangent and cotangent directions that before would be a bit taboo because clearly the tangent bundle is one thing, the cotangent bundle is the other thing, and they don't mix. Once generalized geometry came in, we realized, okay, now everything's packed together, so you can actually put tangent and cotangent in the same packaging, and we can actually exchange these things. And the framework that kind of explains mathematically this thing that the physicists have been saying for a long time is just this thing of saying that with the specific choices that Matai and his group were making, T-duality would be an isomorphism of current algebroids, too many parentheses, an isomorphism of current algebroids, namely the S1 invariant sections of T plus T star of both sides. And it corresponds to picking the coefficient of the angle coordinate, the vector field, d theta, and putting it in the connection form on the other side and the connection form into the vector field. So it flips tangent and cotangent direction, and that is an isomorphism of current algebroids. So now, whenever you have a structure here, that's S1 invariant, you can just use this isomorphism to give you a structure there. So that's another way to interpret the Busher rules, for example. But now, at this time, we're kind of really concerned with, say, generalized complex structures, generalized G2, generalized spin 7, metrics, all sorts of things, Calabi-Yau's. So now, every time you have a structure on this side, we can just push it to the other side. So it's a general thing you can do. So you don't have to write a paper for every new structure that you put on the left-hand side. Oh, this one also goes. You don't have to do that. You can even say, well, but if I have a curvature flow, what happens? If you define everything in terms of T plus T star, then the curvature flow should also go to the other side. The only time when things can go a little wrong is if the instruction T plus T star also requires some compatibility with the anchor map, for example, because the anchor does not get preserved because you switched a tangent direction for a cotangent direction. So if you had a Poisson structure, for example, that lives in T plus T star, but you T-dualize it, you just get a Dirac structure. But that's something to keep in mind. So that was like I think at this stage, the theory of T-duality is very neat. Like, of course, there's way more, but this part of the theory of T-duality is very mathematically very neat. It's like I came to a conclusion. One thing to keep in mind from this point of view is that T-duality happens to the manifold, and the structure comes later. So it's not like, what's the T-dual of a Calabi-Yau? So first you do T-duality to the manifold, and then you can put piece by piece of the structure of the Calabi-Yau, so first the complex or the symplectic or the metric, and see how that goes to the other side. It's not something you should try to do in one go, transport everything. So that's an important thing to keep in mind, that at least from this point of view, that's how things go. What if? So, of course, the story doesn't stop there. What if you have structures which are not invariant? So that's something that Matai, again, got busy with. And he started proposing that the T-dual should be exotic round algebroid. So essentially, from what I got of the papers, I didn't check recently, but you kind of average the structure and do T-duality to that average. And then tensor again with the line bundle, and then the T-duality to the average of the tensored part, and you kind of try to recover Fourier modes of your non-invariant structure, something like that. And then you just collect all those Fourier modes. So it really should be like, there's a downside to that, which is like that nice thing that you start with a structure of a certain type and transport it to something of the same sort, and the other type gets lost. If this picture, you somehow just can try to get the same sort of information packaged in a much less convenient way on the other side. So it's not very clear what you can do in terms of transporting structures, but that's the context of structures which are not invariant, which is a valid question. That's something that we thought about a whole bunch. I think a number of people thought about that. If the structure is not invariant, what can I do? Another thing you can ask is, what if the circle action is not free? And if the circle action fails to be free but has discrete isotropies, so mostly have circles, but sometimes you get like a Zn isotropy for a point, then Bunke and Schick again came back and tried to describe what the T-dual should be. And essentially, when you have isotropy, your circle acting becomes smaller. And because of this inversion, R goes to 1 over R. In the other side, you'd expect to have a much larger circle over one point. And the language that they came to describe it, to describe this phenomenon, was this language of orbit spaces. Again, you have the same problem, that how do you transport structures to the other side? Like, the other side became a bit non-geometric, and then if I have something nice on the starting side, what does it become on the other side? So you can describe the spaces, but the transport of structures that was so nice when it was free circle actions kind of gets much less clear. And what if there are fixed points, real fixed points, not just isotropy? And an example that you have here, it would be if you have, say, a sphere. You can act on the sphere with the circle, and the quotient is going to be an interval. And then you see that because of these Busher rules, R goes to 1 over R, clearly the circles are becoming smaller. It doesn't matter how you think of it, the circles are collapsing at this north and south pole. So if you try to do a T-dual, no matter what you do, you're going to get these circles of infinite radius. That seems to be something you cannot avoid. So the T-dual to this ends up being like a very large cylinder. Which has an incomplete metric if you start putting metrics on this. So like, of course, T-duality first is the manifold and then all the structures. But if you start putting a round metric on the sphere, for example, then you can go from here to here following a geodesic in finite time, and the same time is what's going to take you to go from here to here. So it's an incomplete metric. You get to infinity too quick, because the circles here, the radius is 0, and here the circle became, the radius became infinity. And if you think about it, what's going on, essentially, we do not know what to do with these points, the fixed points. The effect of doing this was effectively, what I did was remove the point, like there's no difference. Remove the point and do T-duality, or keep the point and say that the circle went to infinity and that point has no T-dual. So, a bit unsatisfactory. You can also think of the same thing. I cannot make the drawing, but you can make a picture for CP2. CP2, I'll pick like a circle action that say has fixed point along 3 lines. So line 1, line 2, line 3. So that's just rotation on, in affine coordinates, just rotation on the coordinate planes. The quotient is going to be a triangle. And then here you see that these lines are fixed points for at least one of the circles for your torus action. And because they are fixed points, if I try to do T-duality, some of the circles have infinite radius. So in the end of the day, I really only get like the interior of my toric variety. I lose all the information about the edges, and then we start thinking about it, and all the toric varieties look the same because they're all like polygons, and now I'm removing everything that happens at the edges, so I just get the C star to the N part of the toric variety, so all of them would look the same from this point of view, so it's a bit underwhelming if you try to do it like that. And then you start introducing more language to try to recover the information. So even though I would like to say T-duality is something that you first do to the manifold and then you put more structure, apparently just looking at the manifold, I lose too much and I have to kind of try to recover that somehow, and then start hearing words like superpotential, holomorphic maps, Landau-Ginzburg models, non-commutative geometry. All of that is extra structure that you put on top of your manifold. So it's not something that I could just say CP2 as a manifold this. So I have to think of CP2 already as a Keller manifold or a Fano variety or something. So what I would like to tell you about today is first just recall a little bit what the usual T-duality is. I would like to try to deal with these fixed points. So I like compact manifolds, so I'd like to get compact manifolds as a result. So something fun is going to happen. And the thing that will allow me to get compact manifolds, the result is going to be that I'll change the tangent space into something else. So the Lie algebras will come in, and it's going to be log tangent spaces that will do the trick for me. Once I introduce them, I'll tell you a little bit about how log tangent spaces interact with torus actions, and you see that they are nicely compatible with torus actions, also with the quotient by torus actions. And then I'll be ready to talk about T-duality fixed points. And at the very end, I'll tell you something about the lifting question, which maybe at the moment it's not clear what it is. But just to look at these examples here, say the CP2 example, one thing that you might like, it's good to keep in mind is that the usual T-duality has this exchange of curvature with three-form flux. In CP2, we kind of understand what the three-form flux is. Should be at the degree 3 cohomology class. There is none anyway, but like in manifolds in general, the three-form flux is not something that I'm going to change. But there's a question, what is the curvature? I myself don't remember ever hearing what the curvature of the torus action on CP2 is. Something that I was just not aware of. I don't think people talked about curvature for torus actions with fixed points. So like if I want to switch the tree form with a curvature, I have to actually come up with the notion of curvature to switch it with. Like right now it's missing. So let's just go through T-duality first in case you guys didn't hear about it. But if you didn't hear about it, Ho is there, so you can ask him. Don't ask me. So let's go. T-duality, the original one with this whole topological T-duality business. So first, it's a relation. So if you give me two torus bundles over the same base, I can tell you when they are T-dual to each other. And this is the definition. So they are over the same base. Hopefully the base stays B all along the talk. You form this correspondence space, which is the fiber product of the two torus bundles. Here you have a three-form H, there you have another three-form, and you require that on the correspondence space it should be exact. So the difference, and I'm not writing the pullback maps, you can keep track of that, but essentially H lives here, and because I have this projection map, you can pull it back, and similarly, so I'm not going to be writing that. But we require that the difference should be exact on the correspondence space, and that if I think of f as picking some directions in the fiber of the torus direction here and some fibers in the torus direction here, it should give me a non-degenerate pairing between these two torus directions. So that kind of makes sense of calling the one torus dual to the other torus, because this f is giving you the duality. So it's not as if I start already with T star automatically being the dual of something, but somehow f is what gives you this duality relation between these two things. So yes, that's how people like to that's the construction of F's linear matai. So they pick a very specific f. If you restrict to the torus, it's going to be something like that, but it can have, there's nothing that says that f cannot pair non-zero with two vectors of this torus here, or with two vectors of that torus there. So there'll be a part that's in the fiber of the two, and that's going to be acting like the curvature of the Poincare line bundle, but it doesn't have to have just that. And that's a bit of what Bunke and Schick use to produce all these other T-duals as well. You can play around with it, and you get a whole bunch of other ones. And the example, so getting back to that question, the deconstruction that these guys produced in 2003 was essentially that if you give me a circle bundle over a base, pick a connection and call C the curvature of the connection. My connections here are real, so I'm dropping the imaginary numbers. I can also write my invariant three-form H as something like that. There normally is the condition that H should be an integral class. Once you require that, this coefficient here becomes an integral degree 2 cohomology class, which you can use to produce another circle bundle. So you produce a circle bundle which has that as a curvature, and that's going to be the candidate T-dual circle bundle. You have to also tell what the three-form is, so they just write that one there. And then if you pick this specific f, which is the one that's going to give you the curvature of the Poincare line bundle, then that does the trick for you. You didn't have to pick that one. So in principle, you can start multiplying. If I wanted to get a multiple of this one, so multiply by any number, not any non-zero number, I can play around with that just by putting constants in front of here and in front of here. So I don't have, even in the context of having T-duality, I don't have to have a bundle of primitive Chern classes to dual to a bundle of primitive Chern classes, something like that. I can multiply that by whatever number I like, and also divide. As long as I keep on within the integral cohomology, I'll be able to construct an E tilde bundle, and I can do that. So there is, within T-duality, if you give me one space and one H, I can produce an infinite number of T-duals right away. Some people like to put some sort of unimodularity, so it requires that the coefficient here should be 1 instead of some constant lambda, and that would narrow it down by a bit. Still, there is the issue that you can multiply by -1. So even then, so the orientation of the T-dual is not determined by T-duality relation. So I think these examples I already kind of talked to you a little bit about. So this S1 acts on the sphere, and you have this issue with the fixed points on the north and south pole. T2 acts on CP2, and you have these fixed points, and these don't fit that story that I just told you because of all these fixed points. We missed the notion of connections and curvatures because you have circle actions with fixed points, so it's not very clear what a connection should be. It kind of would become degenerate at the fixed points. And similarly, I'm unaware of somebody defining curvature for this kind of spaces. And my take on this is that you should take the geometry of the fixed point set into account when trying to find T-duality, especially if you want to remain compact. So somehow the fixed point set should come into play if you want to change it in an interesting way. And that comes with this concept of log tangent bundles. This is something that existed already for some time. So there are 3 versions of log tangent bundles that I'm going to talk about. The first one is it's just for a real manifold. So if you give me a manifold with a codimension 1 submanifold, everything real, I can consider vector fields tangent to the boundary, or so in this case, the codimension 1 submanifold is going to be the boundary, but it didn't have to be. So this is an old thing that, I don't know, Melrose is related to that. So that's a name that I associate Mazeo and Melrose. They wrote a book. what you observe is that this kind of thing, locally, you can write down generators. So you have all these guys here. So x1 is supposed to be the variable that x1 equals to 0 gives me the boundary. So all the other vector fields would be tangent to the boundary, and x1 itself would be normal, but then if you multiply by x1, it vanishes at the boundary. And these vector fields generate all the vector fields which are tangent to the boundary over C infinity of m. So it's what's called a free projective whatever, so it gives me a vector bundle, Serres-1 theorem. And not only that, but because they're all vector fields and they're defined by some sort of invariant condition being tangent to the boundary, their Lie bracket is again of that form. So not only it's a vector bundle, but it's a vector bundle that inherits a Lie bracket from the vector fields, so it's a Lie algebroid. And from this point of view now, even though I write x1 ddx1, in the Lie algebroid, this guy here is just a symbol which represents a generator. So it doesn't vanish on the boundary. Only when you apply the anchor, it goes to 0. But this is a frame for my Lie algebroid now. So this is called the real log tangent space or the B tangent space, and I'll denote it by this A for algebroid del M. And I can take the dual and you start seeing something interesting. Because this vector field vanishes, the dual to that is a d log x, which has a pole. And the other guys just appear as they are. So this, in principle, I'm allowed to write them like that. They're all smooth forms on the Lie algebroid. And I'm doing this for a codimension 1 manifold or a manifold with boundary, but if you had corners, you also have that working as well, except that you have more of these singular generators. You'd have x1 ddx1, x2 ddx2 for as many hyperplanes as you have coming to your corner. So that's something to keep in mind. So when I look at the triangle, for example, it's a manifold full of corners there, so I can talk about the log tangent space for the triangle. The same picture can be done in the complex setup. So if I have a complex manifold, so that again has been known for a long time. Like Wells has that as an example in his book, so I have no idea how old this stuff is. If you have a complex manifold, in a codimension complex submanifold, you could look at the vector fields which are tangent to D, but because you're doing real geometry, that's no good. So it's better to look at the real vector fields which preserve the holomorphic ideal that defines D. So what do I mean? So it's good to give like in local coordinates, it's something like this. So Z1 is supposed to be locally the variable that cuts out this submanifold D, and I'll get a Z1 ddz1, similar to what I had before in the real case. The other complex variables just give me vector fields which also preserve D, also preserve the ideal. And all the Z bar coordinates, they also preserve the ideal, because if I take ddz bar of dz1, I just get 0, so it also preserves. So there's a lack of symmetry. It's not a Z1 ddz1 and a Z1 bar ddz1 bar. But that's something you can do, and in complex geometry, sometimes they really focus just on the holomorphic part of it and ignore these last terms here. But essentially, that's the complex version of the B-tangent bundle. So we have here a new Lie algebroid, which has been known in complex geometry for a long time. It's called the complex log tangent space, and now I'd like to write AD, just like before I wrote A boundary of M, except that I have to keep track of this ideal. Instead of just remembering what the submanifold is, even though like if I'm in a complex manifold, the holomorphic ideal defining the complex is like unique, it's well defined. But there is something about keeping the ideal that defines the submanifold. That's the important information. And you can look at the dual, which again gets this singular guy here, d log z1, but the dz1 bar is just there nicely on its own. And maybe the one thing is that it also works if D has self-intersections, just like before it also worked if you had corners. So like for CP2 with these lines coming about, so these are codimension 1 submanifolds with self-intersections, you can develop this theory and you can talk about the complex log tangent space of CP2 with those lines. And I guess maybe the interesting thing is that M didn't have to be a complex manifold. So even though I used complex coordinates and everything, the relevant thing in this whole construction was just this holomorphic ideal that defines this complex codimension 1 submanifold. One way to get that is just if you have a complex line bundle and a section transverse to the zero section, you already get this complex ideal from that section. So you don't need the whole holomorphic geometry to talk about this. So even though this description here with all these coordinates and the other coordinates, it all looks very holomorphic, you really only need a codimension 2 real submanifold and a candidate for the holomorphic ideal that defines that submanifold. Once you have that, you can play the whole game and get your complex log tangent bundle. I'm not sure at which moment that was realized. Marco, do you know? Anyway, so, okay, this one for sure, it was Marco and I who did it. We can kind of go one step further and try to get something real out of the complex log tangent bundle. Because there was this issue here which was a bit annoying, that there's this lack of symmetry between Z1 and Z1 bar, so it does not come from a real object. And I would like to do real differential geometry. So again, I do something similar. I start with a manifold, and now I'll have, again, the same D, kind of more or less the same D as before, but before what I had, let's see here. Before, what I had roughly was the coordinate Z1, which defined D as a complex submanifold. Now I'd like to be able to have a real thing that does that for me. So instead of having Z1, I'll put Z1, Z1 bar, which also defines these. Also, the zero locus is also D. So it's Z1, Z1 bar, R squared, is some sort of measure of the square distance to D. And the correct way to describe that is to call it a Morse-bot function, which vanishes along. So that's the collection of words that describe what R squared is for you. And that's what you need. You need to have like this principal ideal that's locally generated by something like this. One thing that's interesting to notice is that I have the ideal generated by Z1, Z1 bar. I do not know which one is which. So it's not as if I know that this guy is the complex and this one is the complex conjugate. Like in principle, if I have R squared, I get to choose which one I'll call Z and which one I'll call Z bar. So there's like I can go from Z to Z1 times Z1 bar, but going backwards, I have to make a choice. So locally, things get better because now I have both, when I look at the vector fields which preserve this ideal, I have both the Z1 did the Z1, and Z1 bar did the Z1 bar, so it became symmetric. Because the function itself, R squared, is a real function, instead of looking at the complex thing, I can actually look at the real one, and I get R ddr, distance to 0, dd theta, which is the vector field which rotates around, and the remaining coordinates. So these are the guys which preserve R squared. So everybody else is going to be generated by these vector fields over C infinity function. So again, I get a Lie algebroid, but now with two singular generators, R ddr and dd theta. And that does mean that R ddr and dd theta over the divisor are non-zero. So only when I project use the anchor, they become 0, but when I'm just looking at the Lie algebroid point of view, this is a frame for the Lie algebroid, including over D. And if you think of having circle actions, having this dd theta, which also doesn't vanish over the fixed points, starts to become like an interesting idea. This is called the elliptic log tangent bundle. And I can look at the dual space, which something I prefer to use forms than vector fields. So I have d log r as a generator, d theta as a generator, and the other guys as well. Okay. And again, this was the case for D being a codimension 2 submanifold, but if it had transverse self-intersections, just like in the complex case, it would also work. You just get more of the singular generators. Yes?
So imagine you have a plane, right? So you just basically remove a vector field which vanishes at 0, right?
So it's not the vector fields that vanish at 0. If I was, that's an excellent question, because that's something that requires some thought. So if I was, say, on C, I guess I need a codimension 2. So let's say I was in C, and my D was just 0, just the origin. So am I looking at just the vector fields which vanish at the origin? That would be a question. But I can start writing vector fields that vanish at the origin. I have x ddx, I have x ddy, I have y ddx, and y ddy. there's no relation between these at 0. I cannot pick 2 and ignore the rest. Once I start, so that's the problem. Like over 0, they are not like they are all independent, but once I start going away from 0, they're relations. So that doesn't give me a vector bundle. So that's the point of introducing this whole idea and so on, is to pick the correct combination so I get back into having a vector bundle. So
Yeah, but you basically remove certain values and then it's forms a closed loop bracket in your backend.
that's right, yeah.
Okay, but then the next question, does it exist another manifold for which this weird stuff is a tangent bundle? Can you do some change the variable right on C, you should be able to do some over or whatever.
So the question is, if I can find, so right now I have M with D, and the question is if I can, say, find a map either way between this and just another manifold, which would be an isomorphism between the log tangent bundle on D and just the tangent bundle here. It is a little tricky because like here, like at least one direction, here I have some vectors which are actually 0, right? Like this is 0. So if I try to pick a map to N, it's going to send 0 to 0. So it's not like, it's not going to be this isomorphism at the tangent level. So the map would have to be singular. So the derivative of the map, like the map cannot be a diffeomorphism, it have to have some singular derivative to cancel out the vanishing of the vector field and give me something nice.
It looks like if I look at your RDR, I can imagine that I just wrote R square or whatever, and it looks like some maybe it's wrong.
I'm not sure if like so. I think we have to think a bit about that. Like, it's not the question. It's a good question, and just what's the correct framework to get it? To like what should be the hypothesis around the question? Because you cannot just have a diffeomorphism between M and N, which somehow desingularizes the 0 vectors. So you can start asking, like, here I have something above Tm, here I have just the tangent space, and I can start asking for lifts of the map, either one way or the other. But then if the map going from Tm to here,
But maybe it's not diffeomorphism, 0 was
exactly, so it cannot be a diffeomorphism. I think that's the point I'm trying to make, that if it's not a diffeomorphism, so going this way to have to be a map with a kernel, for the points that get maps onto D, and backwards they have to be a map whose derivative explodes. I didn't look into those maps. But you're going to get something that is a bit towards that in a second anyway. So not diffeomorphism, but submersions. So that will give you like maybe an idea of the kind of thing we are doing. Sure. Yeah.
Is there any relation between like this, like take the plate with the points, like these the actual rates, and like if you do real blow up at these points?
Yes.
Relation between this and the like third example you have, where you have like the real grid with the blank of the boundary.
That's right. Yes. So that I guess it's a good point. You do have that, so you can do the blow up. I know that I heard this first time from Marco, and as soon as he said, I said, "Oh yes, it's obvious." I think it appeared in Charlotte's thesis as well. I'm not sure, but it's just something that if you have this D, so if you have MD, because D has codimension 2, I can do the real blow up, either the oriented or just the real blow up, and I have a map going this way from the blow up. And now this, either I introduced a boundary if I did the real blow up, or I introduced just an exceptional divisor. But anyway, I get something here. This map here actually is well defined as a map of Lie algebroids, and it's a fiber-wise isomorphism. So it's not yet a diffeomorphism that you're asking for, but it is there. And similarly, like we are going to do that later, but like if you have D with self-intersection, like if I blow up this point here, complex blow up, then I get a new manifold, and the blow down map is again going to be a fiber-wise isomorphism. So you get like something that will come up later in this talk, but the idea is that complex blow up and real blow up, they are very well behaved with respect to the Lie algebroids. So it's quite a lot better than in complex geometry, because it's like it's as close as to a diffeomorphism as it can be without being one, because several points get mapped into the same place. But fiber-wise, like the derivative of the map just is isomorphisms all along, so it can keep on pulling back structure, and if they're invariant, it can push forward as well using blow-ups. So yes.
Yeah, so going back to the example of R2, one of the things which is often discussed in the physics literature is what would happen if you did T-duality with respect to rotations around the center.
Yeah.
So choose further coordinates. And there's a lot of discussion about what that might be. But one way you can think about what to do is we take the coordinate translation, which takes R to log R, then it takes the plane to the cylinder. On the cylinder, you can do conventional T-duality.
Yeah.
That looks a lot like going from R to from DR to D.
You spoil my talk. That's right.
But the punchline is, from the physics point of view, is you need to say whether you're really dealing with the plane or with the cylinder, and it makes a physical difference. From the physics point of view, the key point of T-duality is that the string theory on two T-dual backgrounds should be equivalent.
Right.
String theory on a plane is very different from string theory on a cylinder.
That's right.
There's a lot of mathematical relations.
That's right. Mathematically, it's also different, and technically, what I'm doing is kind of doing the cylinder but calling it a plane. So I think that would be.
One is the covering of another, so if you keep this type of structure, how it makes sense.
Well, yeah. Anyway, so like but I'm not using the exponential map to get the plane to cover the cylinder, right? I'm really doing what you're describing. One coordinate you call log R a coordinate, and it's just that when I did that before, it would become a cylinder, so it goes to infinity, and now I'm saying, well, zeros is still there. It's just that instead of using the tangent space, I'm using this Lie algebroids to kind of make sense of what's going on over zero. So I'm totally changing the geometry of the situation, and this would be the string theory on the cylinder, not on the plane. And I think that that's an important distinction. I'll try to get back to that. So first, that's how I'm going to do T-duality and keep everything compact. So now we know. But also, it's good to keep in mind, because depending on how focused you are in the structures that you're looking at, you might change the plane for the cylinder and not notice. And that's the kind of thing that I'd just like to call attention to. So maybe this is something that helps with like focusing on where your structure really lives. But yeah, that's the idea. So that's good to hear that you guys think about that. You can go from complex to log. Complex, so the one that had just the dz coordinate but not the dz bar, you can go from that to elliptic just by tensoring. So there's a natural map. So here in the complex, you have d log z. Here you have d log z and d log z bar. So there's a natural map going this way. And similarly, these are the dual spaces, so here I can get something going on also, the whole space of form. So I get a map between the Derham complexes of the complex log divisor, or complex log tangent bundle, to the elliptic tangent bundle. And to go backwards, you can also do so. If you give me an elliptic, does it come from a complex? So right now, what I described, it's gone. But what I described is that if you have z, you can kind of do z times z bar, and then you create an elliptic one. So can I go backwards? If I know the product z times z bar, can I get just the z back? And yes, I can, except that that means I'm picking a co-orientation on my divisor. So I need to be choosing co-orientations on the codimension 2 stratum. If I do that, I get a complex one, but that means also that if I make different choices, I get different complex log tangent bundles that maps into the same elliptic one. So going backwards involves choices, and if you think of D as being a smooth manifold, you have 2 choices. If you start thinking of D as being like 3 lines, then I have to choose a co-orientation for each line, so now I have 8 choices. Similarly, I can go from elliptic log to real log via submersions. I think that's the example that Chris was talking about as well, the cylinder and so on, and mapping into the real line with just the positive real line. So if you have a complex number, you can map it into its norm squared. It's a map from C with 0 as the divisor to R plus with the boundary as the divisor. And this, if you look at the log tangent bundle on both sides, it's just a submersion. So even though as a map between manifolds, it has the singularity at 0, between log tangent spaces, it's just a fiber-wise submersion. And that's the kind of map that you get when you take the quotient of C by the circle action. So now we are getting ourselves in a situation in which circle actions with fixed points are somehow submersions. So I can start taking like transverse and make connections on those spaces. And you can repeat that also for coordinates. So instead of just one coordinate, I can have several of them and do the same projection, and that also works in the same way. So I can have, from elliptic to log, this kind of quotients into manifolds with coordinates, and this is like taking the quotient by a torus action that just rotates the individual components in a certain way. Just a side remark, I would like to tell you something about the hyperkähler structure of CP2. I don't know if you have heard of that one. It's underwhelming, I warn you already, but of course CP2 has no hyperkähler structure, in case you didn't know. But you can pick the 3 lines, Z1, Z2, Z3 equals to 0 inside CP2, so that's the divisor that you pick. And you can do the whole business of looking at the elliptic tangent bundle in affine coordinates, because I'm picking this particular divisor, which is the vanishing of the 3 lines. So let's say you're looking at the first affine set of coordinates, then the elliptic tangent bundle is generated by d log Z1, d log Z2, d log Z1 bar, d log Z2 bar. And if I change the next affine set of coordinates, I picked one here, you see that d log Z1 gets to d log W2, and d log Z2 gets that particular combination. It's like an invertible matrix. So they still exist and still non-zero also in the points that were not parameterized in the first affine set. So the conclusion is that this elliptic tangent bundle is actually trivialized by closed forms if I look at the CP2. So it's a bit like a torus. It's not really CP2, it's really like I can give you a collection of closed forms that trivialize the whole thing. And because it's a bit like a torus, I can do like the hyperkähler structure they have on a torus, for example, this one here. The standard flat structure and the standard flat complex structure, and that gives you a Calabi-Yau structure on CP2 with the elliptic tangent bundle given by those 3 lines. And if you do it well, I don't know if I did it well, but like the projection onto the projection taking the quotient by the torus action should be like a special Lagrangian fibration.
This is like hyperkähler structure C star 2, right?
Exactly, yes. Except that now, like I think one of the difference, like I'm telling, like C star 2, and as I said earlier, all the toric varieties look the same from this point of view, and the difference is just how we are compactifying it. So if I just think of it in terms of C star, it always looks the same, it's just a torus, and that's the end of the story. But you can put like interesting geometry in the compactification, the divisor behavior. So I like to think of it like if you have a Riemannian manifold, a complete one, you can look at the exponential map, follow the geodesic until it's minimized, no longer minimizing, and that makes your Riemannian manifold isomorphic to a star-shaped domain. Except that you have to see where the cutting is happening. So if I remove the cutting, then all my Riemannian manifolds would be rather boring. They're just like star-shaped domains. There's no topology, no nothing. So somehow the divisor structure, that's where the singularities are happening, and making the manifold interesting is a bit lost if I just think of it as just C star squared. Because all the 4 two-dimensional toric manifolds are C star squared from this point of view. Okay, so let's kind of try to pair these 2 things together. Jesus, Ben. Okay, so like I should nail the time. That's a very important thing. So let's try to put these things together. So not all torus actions will do the trick. So you have to have ones that are actually compatible with this whole story that I've been talking about. And by the shape of the maps that I've been using, you can already guess that it should be something that picks. So like the first few Zs here are supposed to have norm 1, and the other few Zs have they're just complex numbers. And the torus should act just by rotation. So like I'm asking that an action is standard if inappropriate coordinates is just rotation on hyperplanes, independent rotation on hyperplanes. So this is a very restrictive type of action. You could call it boring or something like that. We prefer to call it by some name that had, it meant boring but didn't sound so bad. Because, you know, maybe this action is actually a perfectly nice action, you know. Anyway. So an example of that kind of action is if you have an action of Tn on a manifold with double dimension, then it's automatically standard, just because you can linearize it in the fixed points and so on. If you have a circle action on a manifold, you can just check by hand, find a fixed point and check what the representation is, and should be like trivial, 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 and one non-trivial. Then it's a standard. If you start having higher dimensional torus, which is not like all the way to half of the dimension of the manifold and not just a circle, then you have to pay more attention. It's a bit more work. It involves finding a matrix and deciding something about it. So the proposition is that these things are well related. So if you give me a standard torus action, the set of fixed points or the set of points with non-trivial isotropy will form an elliptic divisor. So just the action itself gives me the structure of the device, gives me the idea that I'm looking for. And once I pick that particular elliptic divisor structure, the action becomes just an immersion. So there's no like infinitesimal generators that vanish anymore. So they're all non-zero, including at the fixed point locus. The quotient is going to be a manifold with corners, and the quotient map is the submersion of Lie algebroids, just like the examples I was talking before. So standard actions are good. Once you have a standard action, now that you have this, the infinitesimal generators give you this constant rank subbundle, I can pick a splitting. So I can actually find a connection now, which is a splitting for that map. And once I have that, I can talk about its curvature, which is the derivative of the connection. And just as in the usual case, the curvature turns out to be a basic form, but it's a basic form of this type here, right? So the base manifold was a base with the log, the B tangent structure. So the curvature in principle is a singular form. It can have some d-log coefficients on it. You can always change your connection so that this d-log coefficients disappear and becomes smooth. So that's a nice thing. So that's the result. If you have a standard torus action on a manifold, you can always pick a connection for which the curvature is just smooth. And now I'm in the situation that I can start talking about T-duality, because to do T-duality, I would like to pick an edge which is smooth and switch with the curvature of a line bundle, which hopefully should be smooth so I can actually do the switch and not get something weird. So that brings me to T-duality with fixed points. And just all that I have to say here is just that you can do what you did before, and now things make sense. So now I have the notion of connection, I have the notion of curvature. The definition happens at the B-tangent bundle. So right now, I need these ideals hanging out. I have this F, which should be an elliptic form, not just a usual form, but the rest of it should satisfy the correct conditions. These T's, they also are non-zero over the divisor, so it's all good. So it's the same definition, except I switch my forms to log tangent forms. So I have a definition, and as a mathematician, I'm happy. But then we also have existence, and the similar results that we had before. Like if H has only one leg on the fibers, so there is always this kind of requirement that it should not have too many legs on the fibers, then the same construction of Matai still works in this case, and that's because circle bundles, well, circle actions on manifolds are also classified by age too, even if they have fixed points, as long as they don't have discrete fixed points. So that's a result of Heffliger and I forgot the other name, but anyway, check the paper. So we can actually figure out, like, you can actually do the T-duality, and it's classified by the kind of object that the curvature is giving to you. And you also get a current isomorphism, just like in the T-duality case, which for me feels like this is a nice thing, but now the current isomorphism is between the invariant sections of this elliptic tangent bundle and the sections of the elliptic tangent bundle on the other side. Okay, so just like T-duality before, and this is the moment in which, like, I look at you guys and think, you know, brilliant, got my isomorphism. Structures on this side can be transported to structures on the other side, just like before, like clean. I do understand that maybe some of you had not heard of this elliptic tangent bundle before, so maybe you don't care so much about it. So then I have this feeling that maybe I'm just like that, you know, taking a tangent and feeling that it's so peaceful and quiet out here. Still, maybe not. I hope that some of you guys appreciate some of it, but maybe you say, oh, but it's completely different from the plane. I'm interested in the plane. Let's get an example. CP2 that I was talking about before. So the torus action on CP2 has a triangle as a quotient space. The cohomology of the triangle, the degree 2 cohomology of the triangle, which classifies the line bundle, the torus bundles over CP2, vanishes. It's contractible. So there is no curvature to talk about there. H3 of CP2 is also 0, so there's no twist to talk about. So if I try to switch the curvature in the twist, like there's nothing to do here, and then I just get CP2 itself T-dual. Yeah. So maybe that one was not the example that I was looking for. But one thing that I mentioned before is that T-duality doesn't see this issue of orientation. So I can do the same things, f is equal to 0, there is no h, there's no nothing, but I can flip orientations, and CP2 is actually also T-dual to CP2 bar. It's a fine distinction. I think most people don't know what that means, but CP2 bar does not have a complex structure. It's a weird thing. Like most people think that, oh, it's all good, the I, minus I should be certainly a complex structure on CP2 bar, but no, CP2 bar is a completely different beast, and it's not complex, it's not symplectic, and yet they are self-T-dual. They're T-dual. They're T-dual. Yes?
Provocative, since you were doing quotients. So I will buy what you are doing if you will convince me that T-duality commutes with a quotient, right? So CP2 is a quotient of whatever C3. Your funny T-duality on C3, and whatever your generalized quotient, would it work?
I have to say, I did not think about like this construction of toric manifolds. I expect it works, but you would have to like.
You have to presumably modify everything, because if you modify everything and not all your construction works and diagram is commutative, then it sounds good. If something goes bizarre,
Then it's really good, right? Like when it goes bizarre is when we kind of thrive. It's not when it's the expected shit. Yeah. Anyway, so one thing that happens is blowing up. So I didn't do what you described, but blowing up, which is also something you can do if this toric picture it's actually compatible with T-duality, because I already talked about how blowing up gives you isomorphism of algebroids and so on. If you pick fixed points of an action and blow them up, you get an action on the blown up space. So you can blow up the base as well, blow up a corner, that means like cuts in the corner. So these toric pictures happen, the toric description of blow up kind of comes in and it's all compatible, so that's a good sign for the question you're asking. But there's just this one thing that's blow up in the elliptic context is orientation blind. So to do a blow up, what I need is to have a holomorphic ideal defining that point. And at first, I just have the R squares. I have R1 square, R2 square, etc. And I get to choose if I want to say Z1 or Z1 bar as the complex coordinate that's going to give me the holomorphic ideal. So every time I have a fixed point that I want to blow up, or like a component of this divisor that are intersecting I want to blow up, I have some freedom to decide what I'll call the complex coordinate that vanishes there and what is the complex conjugate. So every time I get to choose if I do a blow up with the standard complex structure, so to speak, or one with opposite orientation. So if I start blowing up CP2 or CP2 bar, all these manifolds are obtained in that way, and I get to choose how many I did with the correct orientation and how many I did with the opposite orientation. But it's all fiber-wise isomorphisms and everything, so they're all T-dual. All these guys are T-dual. And that's an interesting feature because like somehow the original T-duality, you allowed for topology change because it had this edge hanging out. Here there's no edge and there's no curvature, and I'm getting topology change. One way is because I'm completing with the divisors in a different way. Another way to think of it is that this theorem of Heffliger that says that the circle bundles or torus bundles are classified by H2, there is an extra thing that they say is that the locally equivalent torus bundles are classified by H2. And these guys here are not locally equivalent. Locally equivalent would mean that I can find diffeomorphisms in the neighborhood of every fixed point so that the action always looks the same. So that's not the case here. So they are non-locally equivalent, and yet they all T-dual to each other. So there's a new source of topology change, which is not from the curvature and H-flux, but from local topological information around the fixed points. And if you remove the fixed points, you don't see any of that. It's just C star. So it came from non-locally equivalent actions, the topology change, a new source of topology change. And just to finish, I'll look at that. I'll just like use 5 minutes without even asking. So I'll just kind of touch the lifting question. It's a bit that Chris already talked a little bit about or asked about. Let's say I had a complex manifold, I had D, a complex submanifold, and I looked at the associated elliptic divisor. One thing that happens here is that the complex structure on M, which is the one that maybe I was originally interested in, maybe M was a fun variety or something, it automatically lifts to a unique complex structure on the elliptic tangent bundle because of all this compatibility of being complex, submanifold, etc. So this elliptic tangent bundle itself becomes again a complex vector space with an integrable structure, which is uniquely determined from the one you had to start with. So because it's so natural to do that, you might not even notice you did it. So when people in algebraic geometry are doing like log geometry, they make very little distinction between the original complex structure or the log complex structure because they're all kind of related to each other. So like there is a good understanding that we didn't change anything. But I would like to say that you did change something, you put your complex structure somewhere else. And just looking at the complex structure, you might not notice that, but there was a lifting question that just happened here. If you start doing the T-duality, from my point of view, because you have these fixed points and everything, the correct place to look at is the lifted structure. Pick the complex structure that was on this Lie algebroid, you form the corresponding current algebroid, and then you T-dualize it. So that gives you a generalized complex structure in the dual space, which is just a generalized complex structure on this Lie algebroid. It's not something that necessarily is a lift of anything. It might or might not be. Like in principle, it's just something that lives here, and that's the end of the story. If you're really very specific about your choices, it could be that actually is a lift of something, and then you say, well, great, so it's good to see that we can have that kind of example. So the complex structure on CP2 can be T-dualized to one of these that we call stable generalized complex structures, which would have type change. It would be complex along the lines and otherwise be symplectic. But that's for very specific choice of F. And generally speaking, what you expect is just to have a generalized complex structure on the T-dual, like on this current algebroid here. It's just good to be aware of it, because if you start lifting willy-nilly without realizing, the T-dual structure could be weird, and then the only way to deal with it is just by removing the fixed points and looking at C star. So at least here we kind of have a rich topology appearing on non-complex manifolds. All the CP2 bars, they are non-complex manifolds, except for like very specific cases. And there is like mathematical translation of structure from one side to the other. So for example, and that's a common example, if you start with a funnel and you want to do mirror symmetry T-duality on a funnel, like you can pick a toric funnel because those are like easier to touch, like CP2 or CP2 blown up at a few points. Because you're picking complex submanifolds, you can easily be lifting your complex submanifold, your complex structure to the algebroid. So you do your T-duality, and then like what do I do with this? And I guess that you only know which one you're using if you try to look at what happened with the symplectic structure. So when you try to do mirror symmetry to the funnel, typically what they do is say, well, pick the divisor, remove it, because that's fixed points. And then you see that the funnel minus the divisor is calabial, but it's calabial with not the standard symplectic structure, it's a symplectic structure that blows up at infinity in a specific way. So it has a symptotic behavior. So they are not really using the funnel. They have done some lifting there. And the hope is that this is a framework that kind of addresses that issue and keeps everything compact. I think that that's all. Thank you very much for your attention.
ask you to do 3 T-dualities along this 3, I mean, whatever framework you are doing, what would be the result in manifold? By SYZ, it's supposed to be mirror, right? It's not trivial.
Yeah, so C3, right? So you have to tell me the divisors. I guess you're picking the hyperplanes. Then you get C3 with the hyperplanes. Yeah, you get C3 with the hyperplanes. There is no cohomology because the quotient is like this quadrant, so there is no curvature to talk about. I guess you started with a tree form, which was a tree form on C3, so it's a smooth tree form, so it's automatically exact, and so you might quite well get rid of that. It's very similar to what happened with CP2. I think one interesting thing which we didn't do, and I don't know if it's justified, would be to start looking at tree forms which are log forms themselves. Then you have some space for more things to happen, because then you could have curvature and you could have some twist, but then C3 would become more like a torus. In fact, it would be like the 3 torus times R3, and then you can use the tree form on the torus to kind of twist around. So it becomes much more like the usual T-duality if you allow for log 3 forms as the NS flux. Yes?
What's your T-dual for the two-sphere example you started with? And secondly, is there anything you could say about the Boucher rules in this context?
Yes, so the T-dual for the sphere is like if I'm using the points as divisors, it's just the sphere again. And what happens with the Boucher rules is that now I'm using, I should be using, if I'm in this log tangent space, I should be using a metric on the log tangent space. So theta doesn't have a norm that goes to infinity. dd log r doesn't have a metric that goes to infinity. So the Boucher rules are like, if you look at the complement, it's the same as the usual Boucher rules, and it's just saying that if the metric came from the elliptic tangent bundle, it will converge to something that's still a well-defined metric on the elliptic tangent bundle of the dual. So the way that the coefficients should work out should have like a 1 over r, something that makes a d log r a reasonable thing to write down.
So for the two-sphere or CP2 examples, you get back the original metric.
So for the sphere, for example, you kind of like it looks a lot like a torus, as we mentioned a few times. So a typical metric to look at would be something like theta plus d log r. So this is a well-defined log metric. Even though the circles are shrinking, this is fine. So normally, if you have usual metrics, you'd have to put like a 1 over r or something like that, 1 over r squared to make sure that it actually converges and gives something. But this is already fine, and the T-dual would be just like that. So it feels a lot like a torus or something. Underwhelming, but that's what it is. Yeah. Yes.
So what? So you had this proposition where you assumed that the H flux had one leg along the torus fibers. What about more legs?
So the question is, what if it had more legs?
At most one leg on the.
Yeah.
Yes. So what about more?
Yeah. I can't say anything about that. I think that the original case, Matai and his group tried to say something that if you have 2 legs, or maybe, I don't know if it's 3 legs, they also say something, but maybe if you have 2 legs, you can talk about the T-dual as being a field of non-commutative tori. I never understood that. So I think you have to ask them. But there is a proposed model for the dual, and I do not know what you can do in terms of transporting structures from one side to like, what else is the relation except for the fact that you can propose something to be the dual. Yeah.
I was just wondering if you had a counterpart to that.
I didn't look into that. No, like I don't fully understand that result. So I'll not try to. It should be something very similar, but I don't know. Yeah. Thank you very much.